Now I can officially welcome everyone back to school after break. Happy Garbage Day. Got my merch on. One of a kind. I'm hoping that this is one of the last Tuesdays where it's cold enough to need long sleeves. That's what I'm hoping for. But that's probably way too optimistic.
Long sleeves without a jacket could have.
Yeah, I had to wear a winter coat today. You know, it happens. So over break here, I made some scheduling updates that I wanted to make sure folks are aware of. I updated the syllabus schedule for the rest of the semester and updated the printable version so that if you're someone who wants that. Notably in here, I have juggled the due dates of a few remaining things. So today we have Bridge 3 to talk about, which Bladimir is going to lead us through a discussion in just a second. Homework 4 plans are due in Icon next Monday. This is the document. I want you to literally answer the questions in the document and upload it into Icon. If you do not give me enough information to be able to guide you, I may ask you to revise your outline to answer specific queries. If that is needed, then revisions to that will be due on the Tuesday following, so I'm trying to get these back to you as fast as possible. We have one more unit to go in terms of generalized models. That will be binomial and other continuous, not normal things. It's sort of a catch-all. Then we have, I changed it, so we have a formative assessment, a bridge, and then homework 4 due. So you have an extra week to complete homework 4. That we will have more time to get everything situated, and then an FA as the last thing that you do. So homework 4 will now be due on the 28th of April. This is the one that you have to analyze your own data, do your own analyses. It's not a project, okay? It's just a homework. And the instructions for what I'm looking for are available here, the rubric that I want to read, a list of things to include. If you're not sure what to do, if you want to talk to me and Bladimir about strategy or just approach or like how to think about your questions, how to set up your models, that is perfectly fine. This is not a test. This is an experience for you to be able to apply these models to hopefully data that you care about and make this the basis of something that could turn into a project or a poster or a talk or a presentation or what have you. So I just wanted to make sure folks were aware of that. Any questions on upcoming activities or due dates?
Only one.
Yeah.
Are we still having a homework 5 due the last day?
The Thursday of finals week, yes.
Which is fine.
Yes.
Only because you said that the last item was...
Yes, the last regular, like during the semester thing.
Okay, yeah.
So homework 5 is based on example 6A, so I hope to have homework 5 open like well in advance, so you don't have to do it during finals week.
No problem.
Yep.
I just wanted to verify.
Yep. Thank you for the question. And by the way, I also opened up homework 3, which is due in 2 weeks. And by the end of this week, you should have everything that you need to do that. You can certainly get started now. And Vladimir's been through it, so he's ready to help you as well. Yes. Okay. Any other questions about logistics, scheduling, or whatnot? Okay, then just one more thing I forgot to mention. We are on Zoom on Thursday. We're being kicked out of this classroom, so you'll need to find somewhere else to Zoom from or an office. We'll see. All right, Vladimir, you ready to go?
Yeah.
¿Estás listo?
Yes.
Okay, let me see if I can get all the things on the screen at the same time, which is always the tricky part.
Love that giant arrow while you're moving things.
Oh yeah, I set the arrow to be giant and pink because I was tired of losing it. So especially on multiple monitors, it's very helpful.
I need to inquire after class how you did that. I would like that.
It was in the Windows settings, in the mouse settings, I believe, if memory serves.
Okay, cool.
But, okay, so the history of this homework question, let me see if I can make it a little bit bigger, is this is the follow-up to formative assessment number 1, where you found simple slopes and you wrote equations for those. Now I'm asking you to generate the code that would result that equation. Because in homework 3, you're going to get a lot of chances to practice that. Before we do that, I see one more question. Am I grading the homework 4 plans as they come or having a planned date to get those back to everyone? I was expecting the latter. So I want to go through them all in a consistent way at the same time. But I want to get you feedback as soon as humanly possible. Okay, question that. All right, then let's see here. Vladimir, you ready to roll?
Yeah.
All right. Let me put the camera back on so we can make sure you're in the frame since you're taller than me. I always have the self-view taken off of here because I don't like to look at my own head while I'm talking. Okay, there you go.
Thank you, Lisa.
And I'm monitoring the Zoom, so you don't have to.
Awesome. Thank you so
Just have to
much.
chat.
I will move the desk anyway.
There you go.
Hi everyone on Zoom. Hi everyone in the classroom. I hope you are having a good Tuesday.
Garbage day.
Yes, I almost said Monday. Wow.
Stop living in the past.
Yes. So I hope you had a good break too and you are ready to come back to this class. Today we will cover questions from Bridge Activity 3. Half of that Bridge Activity was dedicated to linear combinations, so we will go over those questions. Second half was dedicated to the last content we are covering here, models for count data. Okay. So as you can see here, we prepared a file with the questions, and we have here some of the possible answers. So let me.
Because I think you deleted something on that one
Sorry.
accidentally.
Yes, you were right. Thank you. So let's go there. Let me zoom out.
Getting them all on the same page is
It's challenging.
Yes. Can you see that well? People in the classroom, are we okay? People on Zoom, I'm reading the chat. Okay, so you can participate too. Question 1, well, what I'm saying. The problem was here. Please answer the questions below about the following model from Formative Assessment 1, repeated below. So we know that we have 4 predictors. We have some conditional and unconditional fixed effects. That's what we have to work with. Question 1 was about the predicted y outcome for someone with f equals 2, g equals 3, h equals 4, and I equals 5. So here we can see, well, we can discuss why the correct answer is correct. I think that's better for us. So you can see here that we have, well, the question is related to the outcome, not to the slope. What's the importance of that? When we create our linear combination, you can use R or Lincoln in data. When we create a predicted outcome, we need this one. Do you know what this one is doing?
It's multiplying your intercept by 1, so you're including that in your
Yes.
overall value.
Exactly, Mike. This one means that we are including our fixed intercept in our linear combination. Why that matter in this case? Why that's important? Silly question, or simple one. Yes. Why the intercept matters?
You're looking for the value of y.
Yes, because that's part of the value of y, exactly. So, in this case, given the values in our question, we know that f slope equals 2. F is our second slope here. And now, remember that for linear combinations, all of these numbers are representing slopes in our model. So, you can think about this as spots. We must fill those spots. So right now we know that the second spot corresponds to our first predictor, beta 1, which is f. So we know that f is 2 here, so we put that 2 here. In GLHT, in Lincoln, we create this statement. That's all, right? And the same with the other main effects of predictors until the interactions. These are special because right now we know that those are multiplicative terms, right? And we know, for example, for B5, beta 5, we know that that's multiplying F and G. And we know that F is 2 and G is 3. We multiply those values, 2 times 3 is 6, and that's the value that we use in our linear combination, because that's what R or theta will be multiplying by your fixed effect. Okay? Same for beta 6, interaction between F and H. So we know that F is 2, H is 4, 2 times 4, 8, and that's what we use in our linear combinations here. You can see that theta uses this notation or scheme, and this is for GLHT. Questions? Do you think that's good to understand how this works? Any additional question, please just raise your hand or talk.
So, just to clarify.
Yes.
So we're only gonna put that one in the first beta if we want to include the outcome and if we're looking for that outcome.
Exactly. Question is, what is doing this one? That's including the fixed intercept, and that's important when we are interested in the predicted outcome, because we are taking everything in our model to get our predicted outcome. Now, that being said, let's go to question 2 because.
Can you talk about why the other answers are wrong?
Oh, of course, yes, I will try. So let's go to this option, for example. In this distractor, that's the same, right? We are using the values we have in question 1, but what's different? Yes, we are using 0, so we are not including our fixed intercept in our prediction, which means we don't have all the pieces we need in our model, okay? And that's the case when we are interested again in the predicted outcome from our model. And well, here you can see that we are using 1, 2, 3, 4, 5. However, this term is incorrect because we are not multiplying the right numbers.
You added.
Exactly. So 3 plus 2 is 5, but we know that that should be a multiplication because that's what the interaction is doing here. You can see that this means that we are multiplying those numbers, okay? And finally, yes, here we have both errors. We are summing instead of multiplying here for our interaction, and we are not including our fixed intercept. Okay? How do you feel about this? Are we good? People on Zoom? Are we good? Some thumbs up? That can help us too, okay? You can participate. So, question 2. And this is different because now we are talking about slopes, specifically slope for G. If we go back to our instructions, we know that G is beta 2 spot 3. Okay? So now it says the predicted G slope for someone with F2. When we are interested in slopes, the first thing that we should do, we should put a 1 in the spot for that predictor. In this case, the third predictor in GLHT, third predictor or third spot in theta, times 1. Why times 1? Because we are interested in the slope. That's why. And we need the slope as part of the prediction because that's what we are interested in. Then, what about this other value? Let me ask you, why do we need a 2 in the interaction?
So it includes the slope we're interested in.
Sorry?
It includes the slope that we're interested in. So
Yes, because we have an interaction between the slope we are interested in and the other variable which value is changing. In this case, f. F now will be equals 2, so that must be part of the slope we are trying to estimate. And that's included here. As you can see, here we are defining our interaction and we are saying multiply whatever you have there times 2. Same in GLHT. This will take whatever we have there, the fixed effect, and that will be multiplied by 2. Now, about some other options. See, yes, this is question 2. Let's see this one, for example. Okay, yes, this is a good distractor. What do you think is incorrect in this case?
it has the main effects of F.
Yes, it does, exactly. How can we know that? This one is including as part of the prediction F. No. 1, 2, 3, 1, 2, 3. G. Yes, what's including here is F. Thank you. That's the mistake here. Because we are including, in addition to the interaction, the main effect or the conditional fixed effect of F. But we are not interested in F now. We are interested in the slope of G. That's why that's incorrect. Then we have this one. Oh, here we have,
Two F's.
yes,
One on the far because of the interaction and also up front.
yes, exactly. We are
In
adding
effect.
two incorrect things here. We are adding the conditional fixed effect of f, and we are including the interaction of f here. Let me show you. And as you can see, this is f times h, and we don't even have h in our, that's not related to our g slope. Okay, that's question 2. Questions so far?
Can I make a couple points real quick?
Yes.
So just to remind folks, if I'm asking for like the G slope, the only thing that could possibly turn on in your statements has to have G as part of it. Like just think of it that way. Like if it doesn't have G, it's not eligible. So like it's easy to think like, oh, F is 2, I should plug in a 2 where all the F's are. No, it has to be attached to G. Like it has to be the moderator. And the other thing to keep in mind for Stata users, what your, got to turn the camera all the way down. There we go. I need a short people version here. When you type like F into a lincom, gesture with the mic here. Yeah, like when you say like F1 or whatever, like that thing, you're not talking about F the variable, you're talking about the slope that F is going to be given in the model. And that's the tricky part, is because in R, it's like obvious that you're saying, what, it's going to multiply my slope, that's the number that goes in the spot. But in Stata, it's no, like the variable that you're listing in the lincom, you're asking about its slope. And so it's less transparent, and it's easy to screw up. But thank you. Just want to make that
Yes, agree. Thank you, Lisa. So let's go to question 3 now. Question 3 asks about this f slope now for someone with g equals 3 and h equals 4. In this case, we know that given that we are interested in the f slope, that's the first thing that we look for. So that means f is the second fixed effect in our model, so we put a 1 there. Then we must check our interactions. Are the other variables in our model interacting with f? And the answer is yes, we have 2. F is interacting with g and h. That means that if we are interested in the f slope and we have different values for g and h, we must include those values in our model. Okay? Questions so far? Are we good? Okay, great. Now, let's check some other options. Yes. What do you think is incorrect here? Are we adding more stuff, right? Can we agree on that? Because that's the case. Here, you can see that we are adding these 3 and 4, which are multiplying the fixed effect of G. Is that, yes, G and H.
Just because you have the information doesn't mean you need it.
Exactly.
Those are the main effects, right?
Yeah, those are the main effects.
Yes.
They're not eligible.
Exactly.
They're
Not for that slope.
Yes, for the f slope. Exactly. So then, yes, that was the distractor we had to check. Now, for question 4, we are interested in the predicted h slope for someone with f equals 4. So we know, again, h slope, we go back to our model, we know that's 1, 2, 3, 4th spot. We have our 1 there. Then, for someone with f equals 4, do we have any interaction between h and f? Yes, we have. The last one. So that's why here in the last spot we are including a 4 because we have an interaction between h and f. So let's check some of our distractors here. In this case, what do you think is what are we adding here?
The main effect of F.
Yes, exactly. The main effect of f. Here, this 4 shouldn't be there because we are analyzing or we are getting the estimate of the h slope. Okay? Then other distractor was this one. Oh, this is an interesting one. What's wrong here?
that the 1 turns on the y.
Exactly, our first one. Why? Because this one corresponds to our fixed intercept, and we are not trying to get predicted outcomes, predicted y outcomes. We are trying to get some estimates for our h slope. Okay. That covers the other distractors. Questions so far? Okay.
One question,
Mike.
I don't use data, but
Yep.
if I did not include all the pieces with the zeros, would it still calculate that correctly for me?
Yes.
I think.
I like the zeros because they're good placeholders to help solidify concepts. I get that, but that's the only reason I was asking about it.
Yeah, like in practice, when I write code, I only put in the ones that could contribute so that I could make sure I cover all the things that I need to consider, but I would not include the ones that'll always be zeroed out because they're not eligible.
Okay.
Mhm. So for Stata users, you can omit those zeros here, like these ones, which is, yes, weird to me. Because we don't know what else we have.
Constants in parentheses.
That's true, yeah.
Yes.
Well, yeah, that's true.
When I
Because
first
we have a lot
read
of
this, I was like,
zeros.
Seriously? Seriously, I had to do it this way?
So then, finally, well, for this first half, we have question 5, predicted,
My favorite one.
oh, predicted I slope for someone with f equals 2, g equals 3, and h equals 4. As you can see here, interestingly, we have only one here. Why? Why do you think that's the case?
I doesn't interact with the other 2.
Exactly. Yes, we have only one because our I predictor is not interacting with anything else in the model. So even if we are changing these values, that's not affecting I slope, the slope of I. That's our answer. So let's check some distractors here. This one, for example. What are we doing here?
We included everything except for the y-intercept.
Exactly, Mike.
Appropriately.
We are using our reference values to fill these spots, but those are not needed because those are not involved or they are not related to the slope of phi. That's why that's incorrect, okay? And that's why we have only one in our linear combination. Questions? Do you feel good with this
I
now?
would say that's a great, these are great questions.
It was very helpful.
Yeah, for sure. Yes.
Well, the distractors are built from 20 years of people screwing stuff up and you noticing what's in common when they do it, and there's only a certain, like, finite amount of errors, it seems like. And once you understand those, and you stop making them.
Yes. So great. We did the first half. So let's go with the last, with the final 5 questions. Question 6.
No questions.
Yeah, this is amazing. So this is asking for the use of a Poisson distribution or a negative binomial when the Poisson. Sorry, did I miss one? Oh, many. Wow. I was almost in the last question. Yes. Thank you, Lisa. Didn't realize.
Well, I don't want to, cheat you from your presentation time.
Yeah.
You can't skip ahead.
Okay, thank you. So, sorry for that. Let's go now with question 6. Yes, it is, question 6. So here, we are asking for the use of, okay. What these different things are doing in our model. Yes. So we don't have the question here now.
Yes, you do.
Change.
Which of the following is,
correct?
oh, okay, that's all. Yes. Which of these ones is correct? So we know that the use of a natural log link function keeps the predicted expected outcome between 0 and positive infinity. What's that the case? What are we predicting here? What type of outcome are we analyzing now with Poisson distributions? Is a binary thing? Is an ordinal thing? What is?
Discrete.
Continuous.
It is discrete. We are analyzing counts. Exactly. So, exactly. With counts, what's the lowest possible value? 0, right? What's the maximum possible value?
Infinity.
Whatever you have, exactly. And that's the predicted expected outcome between 0 and positive infinity. And now, but the conditional distribution needed to address non-constant variance should be determined empirically. What does it mean? The second half of this statement. What does it mean?
I'm trying to recall that we had like a C multiplied by lambda. That's what I'm picturing on a slide.
There's a K, but yes.
Or K, sorry.
Same sound.
It's easier than that, I think. Do you remember that last week or the week before spring break we were talking about Poisson distribution and negative binomial distribution?
I don't think they remember.
Okay. Yes. If that's not the case, please just say that, because remember that our first option when we are trying to model count data is Poisson distribution. One of the characteristics of the Poisson distribution is that we have only one parameter in that distribution, so which is lambda, and lambda is describing at the same time the mean and the variance of the distribution of our dependent variable, which it doesn't sound good, right? Because we know that dispersion and the measure of central tendency can be different things. So when we have some models with more dispersion than the mean, we can change our distribution to something known as negative binomial. And we are adding a substantial piece to our distribution, which is what Lisa calls the stretchy factor. Why? Because we know that if the data has, if the outcome has more distribution or more dispersion than the mean, we need something else. We need something to make our distribution stretchier or more stretchy?
Stretchier.
Stretchier. Yes. So the difference between Poisson distribution and negative binomial is just one parameter. The parameter that's making the negative binomial distribution stretchier compared to Poisson distribution. And that helps us to model some outcomes when we have more dispersion compared to what the mean is saying about that dispersion. Okay? Did good? Well, I did it. Awesome. So, considering that, we know that if the difference between negative binomial and Poisson is only one parameter, what does it mean? What's the meaning of that? Do you think that that models with these distributions can be nested? If the difference is one parameter, what do you think?
Just one parameter, no.
Sorry?
No, just one parameter. You can't next it. It's going to next it too.
Yes. Oh, okay. Let me try to explain this. Let's say that I have a count outcome. I'm using a Poisson distribution in my model, but I discover or I found out that that's not correct. So I'm using negative binomial distribution. I'm adding one parameter to my model. That's stretchy factor. Okay? If I set that stretchy factor to 0, what do you think will happen? If I set that extra parameter to 0, I'm saying it has no effect. What do you think? We are going back to Poisson, surprisingly, because the stretchy factor is doing nothing. Doesn't make sense?
So, nested models means one's a subset of the other, and so you can see what the relative contribution of the new thing is and if you need it. And that's what determined empirically means. So we'll go back over that today in terms of what that process looks like.
Yes, we can discuss that later. So if you have questions about this, please raise your hand or just you can ask any question because this is hard, but this is fundamental in the process of learning the next models we have for this unit. So please, if you have questions about this, you can ask them now or later. But the substantial piece of information here is when we are adding or subtracting something in our models, we have nested models, and we can compare those different versions of the models via likelihood ratio test. That's the empirically meaning of this, because we have a test to test if what we are adding or subtracting makes our model better or worse, okay? So, question 7 says, if a predicted count outcome in log is 1.2, what of this option is correct about the expected count? We know that we have logs, no log of the odds. Log of the odds was logic, okay, which is different. Here we are just taking the log of we have the log of the expected count in the model, so we must take the exponent of that to get our predicted outcome. That means that if we take the log of 1.2, we will have this 3.32 here, okay?
Other way. Oh, e to the 1.2.
Yes. The exponent of that is not, the exponent of this is not the same.
That's the exponent when you're evaluating.
Oh.
You don't want natural logging, you want truly the e to a power, exponentiating. I'm not sure if that's what you want to say for that, but yes. Yeah, e to the log. Yeah.
Awesome. So this is just e.
E to the log, yeah, e to that thing.
E the log. Wow, English is amazing. Duolingo. Thank you, Duolingo, but I'm still learning. Thank you. So yes, this other option is if you take this 1.2 and you take the square,
Yes.
you would get that value, okay? But that's incorrect because here we know that this is in log metric. So we must take the e of that to get our predicted count, okay? Question 7. Question 7 says, which of the following is correct in models predicting count outcomes? And again, here we are describing components in our model or the concepts in our models. Counts are discrete integer values, correct. Expected counts are continuous above 0. Yes, because here we have expected counts. And log of the expected counts are continuous from negative to positive infinity. Are we good with that? Different scales in our model. Now, this expected count is in data or model scale?
It's somewhere in the middle, because it's trying to describe the data, but expected counts are continuous, whereas the data are discrete.
Yes, even in that case. Okay, got you. Yes, this is,
Closer to data.
yes, this is not discrete because when you take the e of the log,
I like to think of expected sync weighted average, because that's kind of ish.
Yeah, it's the expected value the model's trying to solve.
exactly, that's the expected value that the model is trying to solve. So that's continuous too. Now, if we go to distractor 2 here, the error here is that the log counts are continuous above 0. That's not true, because we know that when we have a log, that can be positive or negative. And we know that 0 means 1. But in this case, it's not the same as before related to odds ratios. Here, that 1 doesn't mean that we have probability 50-50, for example. Okay, so that part was incorrect in this option. Question 8 says, which of the following is correct regarding distributions for count models? Awesome, you did it. So
I like
congrats.
I like your negative 0 discriminant.
Cough, cough, homework 3 question.
Yes, exactly. So just remember as you answer here that we can use likelihood ratio test to compare these distributions, and this is related to what we were talking.
Empirically determined, that's what this.
Yes, exactly. So good job doing that. And finally, question 10 says, which of the following is correct regarding distribution fit as indexed by the Pearson chi-square over degrees of freedom. This is lecture 3, slide 11. That's the formula. The formula is there, I'm pretty sure. Lecture 3, slide 11. So, in this case, we know that this Pearson chi-square, this value, help us to see or to compare the data observed standard deviation of the residuals to the model expected standard deviation, in which values greater than 1 indicate over dispersion. To me, the numerator is similar to the sum of squared errors.
Yeah, it's what happened in the data.
Yeah.
Is the idea. What
Yeah.
should have happened according to the model is the bottom.
Yes, because in the numerator we have the observed value minus the predicted value. So to me, that's the residual, and we are summing over the square values. Okay? So why this option shouldn't be correct? It compares the model expected. Oh, yes. Here I think that we are inverting the components, which is incorrect. And that's all. How do you feel now? Is it better? I hope so. If you have more questions, you can ask them now or later. Thank you for your attention. That's all, I think. Great. Yes.
See this one better?
Yeah, that's
Yeah. The short people
Oh.
button. There we go.
awesome.
Thank you. All right, let me get my chair back. Because I earned a PhD, so I didn't have a job where I had to be on my feet all day. So, or wear a name tag, for that matter. All right, 1 second, folks. Let me get situated
Or
here.
be in a suit.
Or wear a suit. Yeah, wear heels, pantyhose, none of that.
Yeah.
Yes. So this seemed to go better. I'm glad folks look like this went reasonably well. If you're still struggling with any of these concepts, please let us help you. Office hours aren't just for homework questions. We're happy to come and talk about anything that's troubling you, or you can set individual appointments with us as well. So yeah, introducing some new vocabulary in here. The idea of over-dispersion is new to counts. We didn't have to worry about that before. So let me let's orient us back to lecture 3. Should I assume that you don't have perfect recall of things that we talked about 2 full weeks ago?
Mm-hmm.
Would that be reasonable? Okay, Zoomers, is that reasonable for you too? No perfect recall assumptions of any kind?
What's recall?
Yeah, exactly.
I don't
What's recall? I don't recall. That's pretty good. So we'll start at the beginning here. So the laundry list of things that we've covered and still have yet to cover. The key idea here, in using regression models to predict not normal things, that's what we've been doing this semester. There's distinctions that we sort of glossed over in talking about regression models for normal outcomes. So like the difference between y and expected y. Like we talked about predicting y, and we didn't need that language because y was thought of as continuous. The expected value of y is thought of as continuous, and so there's no distinction that needs to be made. And because it's expected to be truly continuous in standard regression, we don't have to worry about predictions going out of bounds. So we didn't need link functions. So we're adding link functions to solve the prediction of things that have to stop at some point from going outside those boundaries. So if we have, hey, come back here. There we go. So if we have categorical outcomes, for instance, we started with binary, zeros and ones, can't predict anything past that. But binary, the original scale of the data is zeros and ones. The expected value is probability, which ranges continuously from 0 to 1. And then we took that expected value of probability, divided by it 1 minus that became odds. Then we take the log, and then that's our friend logit. So logits are for boundaries on both sides. The question then is, in terms of whether we want ordinal or nominal, what kind of logit or probit that we have. So cumulative means ordinal. Adjacent category is an intermediate possibility that I like that no one uses. And the baseline category is for nominal. So that's when it's like you're dummy coding your outcome. So in these discussions, we worried about what kind of link and whether it assumed order or not. But we said the distribution is Bernoulli for binary, the end. The distribution is multinomial, which is multi-category Bernoulli, essentially, the end. We didn't have to worry about it. So what's new in talking about counts it's kind of the opposite. There's really only one link that would be logical, log, the ant. The question then is, what kind of distribution goes with it? And when I say should be evaluated empirically, that's the formal way of saying, let the data pick. See what the data want. Compare alternative versions and see what fits relatively best. So we have to worry about that aspect of it. Still to come are what to do when you have too many zeros, as another set of distributions that are possible and might fit better and reflect the data better. In terms of your projects, the next unit will be useful to several of you who might be modeling proportions, or things that have boundaries on both ends but are continuous in the middle, broadly construed. So scale scores, for instance, where you have floor and ceiling effects, can be recast as proportions to be used with these models. And in this case, we're going to be back to our friend logit, because boundaries on two sides. But then it's some kind of beta binomial as a distribution, and we'll have to worry about that, along with extra zeros in this as well. I'm going to wave my hands at this one and tell you that it exists. There's an article on your reading list about it, but for censored data, it's a Tobit link with an assumption of a normal distribution. And we'll see this in example 4b, what happens if you have continuous data that are skewed and bounded at 0. So that will be both gamma regression, log normal regression, and what's the other one? Quantile regression. That's the one. It's not technically a generalized model, but it fits in these problems. And then we have hurdle versions of all of that. So some kind of link, some kind of distribution, some kind of regression. That's the big picture here. Okay. With me so far? All right. Then our friend log is the link function. So we're predicting the log of the expected count. That's our model scale. To put it back into the data scale, we need EXP, E to the predicted log. That's the link part. In terms of distributions, Poisson, let me pick this up here, slide 6. Poisson is the starter kit for distributions for count data. It's like the base model if you're buying a car without all the features that are fancy on it. I have never once seen this fit empirical data. Never once. But it's a starting point because we can trick it out by adding like, hey, would you like a fancy stereo? Hey, would you like front wheel drive? Hey, would you like all these extra features that make the bigger model different from the base model? And as Vladimir pointed out, we're talking in this family about nested models. Nested means one is a subset of the other. So you can take a parameter away and it becomes something else. That allows you to see if that extra parameter is helping you or not helping you. So the problem with Poisson is that it says the expected mean is the same thing as the expected variance. So if I just have an empty model, like for instance, this orange distribution here is supposed to have a mean of 1 and a variance of 1. The purple one has a mean of 4 and a variance of 4. Once you add predictors, each person is going to have a different mean based on their combination of predictors, but it's still considered a mean because anybody with the same values would have the same prediction. So if I fill in all of my predictors and I find out that my expected count is 6, that means there should be a variance of 6 around that. When I get up to people who have an expected count of 8, the variance around that 8 should be 8. So they should be lockstep increases of mean and variance, and that typically doesn't happen, particularly when you have small counts with a lot of zeros. So that's why Poisson as the base model is going to be insufficient in practice. Usually we have more variance than the mean. That's called over-dispersion. Sometimes there are no zero values, and we need to fix that, and sometimes there's too many zero values. So we had been talking about negative binomial, which has some ugly formula. Don't ask me what it means. I just copied it out of a book. Okay, don't ask. But the K thing is the thing to hang on to. And yes, I call that the stretchy factor, because in practice, distributions that follow negative binomial tend to have more positive skewness. And so the variance exceeds the mean more than the Poisson anticipates. And the way that this works is that the K is a multiplier. So the variance is allowed to exceed the mean in a quadratic function that this is a weight for. And technically speaking, when K reduces to 0, the log likelihood is undefined, which is why some folks like a different version of the model, but in practice, people just ignore that problem and use it anyway. So negative binomial versus Poisson, we can do a likelihood ratio test for that. Did adding the K stretchy factor that allows the variance to exceed the mean have over dispersion? Did that make the data taller? If so, we keep that one. If not, we don't have to keep that one. It would be overkill. How do we know? We talked about the word fit, meaning lots of different things. What it means in this class, slide 11, very good. The students marvel at Vladimir's ability to memorize my slide deck numbers. I don't even know what these are. So distribution fit was a new idea that we introduced, and this shows up in generalized models to try to figure out if a given distribution is good enough. So it's absolute fit as opposed to relative fit. Like I can say that negative binomial makes the data taller than Poisson, but I can't say that negative binomial is the tallest it can be. Like that's the question, like is it enough? So to evaluate that, we can ask for this statistic called Pearson chi-square divided by degrees of freedom. And I referred to it as standard deviation in your homework. I probably should have said variance because it's squared, but 6 of one, half dozen of the other. The numerator is what happened in the data. What is your actual y minus the expected value of y? Like how wrong is your model on average? That's capturing error. On the denominator is how much error does your model think there should be? And ideally, these should match. To the extent that your data have more error than your model anticipates, this will go positive, and that's an index of misfit. So 1 is what we're shooting for here. Anything above 1 is suboptimal. So we'll have to do a little bit of work to get this out of R. It does show up in certain routines in Stata and in SAS as well. And here's the formula for all the other distributions. Most of them have this available. The one that doesn't is normal, though. So in practice, we can't use this to talk about normality. Yes?
Lisa,
Yeah.
here in this slide, we can see that for Poisson, for example, the denominator is the square root of the predicted value. However, in the previous slide, in the denominator, we have the standard deviation at the expected y. Is that the same?
Yeah, because I put the square out here. So like this is in standard deviation units and so is this, and then I made it into a variance. Like they're doing this in standard deviation units. So this is the square root of this would be, the variance is the mean, so then the square root puts it back into standard deviation units.
Great, thank you.
Yeah. Yeah, and honestly, this class is the hardest on me of everything I teach because of all the different notation systems across people who've described these models and all the different ways they are embedded in the software. Like this is the point where I had to work very hard to figure all of this stuff out. So please forgive my slight inconsistencies in borrowing across these things, but that's unfortunately the reality of it. Take-home message. If this index is over 1, then you have too much variance in your data relative to what your model says. And we'll see the consequences of that in the example that we've been following. Yeah, okay.
Do we care if it's less than 1?
Under dispersion is, yeah, technically possible, and then it would have the opposite problem. So if we think logically about what is the consequence of having not enough variance represented, it looks like your model is too precise. So your standard errors are too small, which means your p-values are too small. And so then like everything looks too rosy. If you have under dispersion, meaning you actually have less variance, less error than what your model says, then your standard errors are too high, your p-values are too high, and so then you're shooting yourself in the foot. Either way is wrong, but depending on what you're doing, one way of being wrong might be more tolerable than another. Okay, is this sounding familiar, at least? Like, I feel like I may have heard this before, is all I'm going for. Not perfect recall, just familiarity. Okay, any questions?
I saw the slide.
You saw the slide. Yeah, it is familiar. It takes layers of this stuff to get in. That's what I know. Like this isn't something you're just like, oh, I heard this one time and I'm good, right? Like Bladimir, how many years have you been TAing this class? Is this like the 3rd time?
Yes, this is my 3rd time.
3rd time. Do you know everything perfectly?
No.
Oh, no. Okay. Yeah, so he's been through this 4 times and he's still picking stuff up. And the same with me. When I read stuff again, every time I pick out something new that I didn't put together the first time. So this is an iterative process, to be sure. But let's jump back into example 3. We were talking about, do you remember the story with this? This was a student's master's thesis. The outcome is number of mean things said during an experiment in which people were deliberately pissed off, and they were assigned randomly into 3 different conditions as to what they should do with that anger. One is whatever you want, that's the control. Try to do some cognitive reframing, which is maybe the better coping mechanism. And suppression, which is to shove it down, don't think about it, which is the less optimal one. And the primary research questions were about how these manipulations would play out differently in people who either do not have a history of interpartner violence or people who do. So that's the story. And the distribution of the original data that motivated this entire example is right here. So this is a fairly classic count distribution. Bunch of zeros. So a bunch of people said no mean things. And then all the way up to somebody said 24 mean things. So skewed, discrete, because these are counts, but bounded at 0. So then the question is, what kind of distribution would characterize this? And if all I had to go on was this picture right here, I can't answer that. You cannot look at a distribution of the data and say, yes, this is what kind of model I need. This is marginal. Our assumptions are not about the data, they're about the leftover data after being predicted. So the question I would have is, to what extent can my predictors of history of violence and experimental condition explain this pile of zeros? Maybe this pile of zeros is all the people who aren't in the bad conditions and who don't have a history of violence. And indeed, if you look at the breakdown by group, that's kind of what happened. Like this middle group right here is like most of them have zeros. So the model is going to end up explaining quite a bit of this zero inflation with the predictors. So I can't just look at data and say, yes, this is zero inflated, this is what I need. I'm going to have to look at what's left over and then figure out what I need. So assumptions are always about residuals, not the original distribution. So in this example, I'm going to have the exact same linear predictor. Remember, that's the term for the fixed effects that go into the model. There are 6 possible combinations of outcomes in this design. It's a classic 2x3 type of ANOVA design. That means I can fit 5 slopes and 1 intercept and perfectly recreate those 6 means. So I know the means are right. The question is, are the standard errors that go with those means right? And that's what the distribution is supposed to handle. So I gave away the end of the story right here. Here's a comparison of the different sample sizes per cell, the maximum count per cell, this observed standard deviation per cell, and then the means in the raw data, and these are the standard errors of the means, which differ because of the sample size and because of the standard deviation. If I look at the green columns, notice anything in common?
All equal.
They're exactly the same. And that's because no matter what I'm doing here, I'm reproducing those 6 possible cell means with 6 fixed effects. They're going to be right. And it's not the same thing as logging the data and taking the mean of that log data. This is the log of the expected mean for each of these things, and that's why it matches. Now the pink cells. These are color-coded so that smaller values are closer to white and larger values are closer to red. These differ. So they differ a lot across the different models because in the raw data, we can see that, yeah, it looks like the counts that are smaller on average have less error to them. Unsurprising, because the closer you are to 0, the less wrong you have room to be. The people that are out to like 24, you have more room to be wrong. The normal distribution says that other than the differences in sample size, all of these standard errors should be built from the same amount of residual variance. But if you look at the standard deviations, like that can't possibly be true. It just doesn't fit. The higher the mean, the higher the standard deviation in most of these cases. Poisson says the mean and the variance are lockstep. And so this one has smaller standard errors across the board that are more homogeneous. And the negative binomial says, no, actually the variance needs to exceed the mean by a quadratic function. And that's why we have greater variability here. So it's the inferences we make about whether these means differ from each other. That is what the distribution depends on. The means themselves are the means. So we looked at, we're using generalized models to fit what would be a typical ANOVA, just as a comparison point. We looked at that in Stata, and we looked at that in R. And I had a note next to predicted outcomes of technical term. Why do I say
You're predicting negative?
Yeah,
Or negative is in your interval. Sorry.
Yep, my interval for what this cell mean should be is negative. I can't have a negative count. So this is telling me that the error around these things is not appropriate. It's too large for this cell. It's probably too small for others because it's assuming that it's constant when it's not. So that tells me just right off the bat, this is probably not a good idea. When I went through the trouble to go through all of the results, though, we'll pay attention to how this changes. The p-value for the 2 degree of freedom interaction between IPV condition and experimental condition was 0.06. So the thing that this student was most interested in was right on the edge, and I'm pretty sure that's what's prompted the conversation. Okay, so then we looked at Poisson. Do you want to go back over the code that generates these things? Yes, because you're going to have to do it in homework 3. So it's not that different, but we're adding extra options to customize things. So the routine that I'm using in Stata, this is page 6, the bottom of page 6 for the Poisson distribution, is GLM, stands for generalized linear models, of which standard regression would be a special case. So agar is my outcome. I have my main effects of my predictors, so I set up these as dummy-coded predictors already, where IPV is 1 if they have a history, 0 if they don't. The control group for none is my reference group for experimental condition. I have N versus C, which means how the cognitive group differs from the none group. N versus S, how the suppression group differs from the none group. And then in Stata, I have interaction terms with these hashtags /pound signs. ML means use maximum likelihood, otherwise it might default to something else. Link equals log, you'll need that. Family equals Poisson, that means that's the distribution. And no log is just don't do the iteration history on the output. That has nothing to do with the link function. I put that in all my Stata packages at this point. So Stata spits out immediately this Pearson chi-square over degree of freedom statistic. It's 4.7. We want it to be 1. So this means we have over dispersion. It means that there's more error in the data than what the model is anticipating. We don't have enough variance in our model, essentially. So that means, practically speaking, I would probably not want to interpret any of these results because the distribution doesn't fit. And that means the standard errors are going to be wrong to some degree. And sure enough, the interaction term that used to be 0.06 for its p-value is now significant to all the decimal places. Yay! No, it's wrong. Done. No cheering yet. No cheering yet. So in R, we got to do a little bit more work to get to the same place. I am using GLM as a base R package to do this. It wants to know your data set. It wants to know family equals Poisson, link equals log in quotes this time. Then it wants to know the formula. Up above here, I made 2 variables that are going to be used in my R program, and I would encourage you to do this too. One is the degrees of freedom based on the sample size, and the other is degrees of freedom based on sample size minus number of fixed effects. You need this one in your homework. I put in both so that you could replicate the results in SAS or Stata if you wanted to, but this is the version that you need. Stata computes degrees of freedom, Pearson chi-square over degrees of freedom for you. We have to do it in R sort of manually. But here's the Poisson model output that we're not going to interpret because it's probably wrong. Here is a manual computation of Pearson chi-square over degrees of freedom. This is the only way that I could find to do it. So if we dig into this, it's taking the model object, model Poisson, so that's what I just saved in this. It's asking for the residuals from that. So it's doing the math for you to say, okay, here's my observed count. What's the expected count given my model, and what's the difference? So that's what residuals is getting. And then it says, what kind? Pearson. There's other kinds. Just that's all you need to know. There's many kinds. And then we need to square it to keep the positives and negatives from canceling. And then we sum it across people. And then we divide by the degrees of freedom, which is the number that I put here so that I wouldn't have to keep computing it. So you change it once and it updates throughout the rest of the package. And so then that spits out the same 4.7 that Stata gave us. So practically speaking, what do you need to change to do this in your homework?
Denominator degrees of freedom.
Yeah, you would need to update that number and make sure that it's pointing towards the right name of your model. Otherwise, the rest of this is just boilerplate.
Now, model persona, just because that's the name of your
That is
model.
what I named it.
Just making sure.
Yep, so if you follow my naming conventions, you'll be fine. If you make up your own, then you have to change it. Yes. And this number is going to show up in several different points, and so that's why I made it an object. So this is my sample size. That's the root of it, and then subtracting the number of fixed effects gets us to the Stata version of that. All right. In R, we haven't talked about this as much as we did in Stata, so let me make sure I've hit this one. To do a 2 degree of freedom walled test, you would put in the interaction slopes that you want and tell it to set them equal to 0. And then this function here will give us, stop it, the hypothesis test for the 2. So this is analogous to the test statement in Stata that does this more directly. So this is generating a chi-square that tests the 2 degree of freedom interaction simultaneously. That's what this means. So, looks like the interaction is significant, but we can't trust the model results yet. To generate predicted outcomes, you'll get to do this in your homework as well. I'm using the prediction function. I'm pointing it to the model. Type equals link. That's going to give me model scale predictions. What is my scale going to be in this example? What's the model scale we're dealing with? Starts with an L. And don't say logit. Say it louder.
Log?
Log. Log. It's log.
Ren and Stimpy.
Ren and Stimpy. I watched the
All
video.
the time. You have no
Yep.
idea.
It's log. It's log. Yep. Link is log. So these are log counts, right? So that's why I'm looking at this and I'm not freaking out that some of them are negative. Logs can be negative. Okay, it's totally fine. Now, in your homework, what would I need to change to use this? This part. Yeah, these are the, what do you want the predictions for? What values of your predictors? So this is generating expected outcomes more efficiently than if we put them into individual GLHT statements, but you can do that too if you want to. But since no one knows what to do with a log count, we would ask for another version, which is type equals response. That's data scale. So these are expected counts. So if we look at these, they're all above 0 because they have to be. That's the point of the link function, but they have decimals. Expected counts are continuous. Original counts are discrete. So these are expected counts. So if I just eyeball these things, it looks like people who are put in the suppression category said the most mean things.
Are we concerned about the negative in the interval on the end or not?
That is a great question. I think I would be concerned, but this is a interval that somehow is not understanding that it needs to stop. I think it's because it's not doing the nonlinear transformation of it. It's just like building it this way. So I would probably not use these intervals, but I would use like that part.
Okay. Thank you.
Yeah, thank you for pointing that out. That's disturbing. I'll have to look into that and see if there's a way to fix it, because that shouldn't happen. Vladimir knows?
Yes, I have a follow-up question because
Yeah.
we are building our intervals assuming that the prediction is normally distributed.
That's what I'm thinking it's doing. I think it's like disregarding, like it's using the same algorithm to make the intervals regardless of whether it needs to reel it in or not.
Got it.
And that would be a problem with the package, not the logic. So I will have to see if there's like an option to make it do something else that's more meaningful to that. But yeah, I normally don't pay attention to confidence intervals, and so like I just disregard these columns. But that is disturbing. This should not happen. And But yeah, I think that's what it's doing. It's just doing a typical confidence interval without paying attention to the boundaries. Yep. All right, 310. We're getting there. So this is a comparison of what we've seen so far. Identity link normal versus log link Poisson and the difference in the p-values. So everything is significant in Poisson, like hardly anything is significant in normal, but we're not happy with either of these things yet. So that would be where negative binomial comes into the story. So the difference then, to fit that, I think this is going to be a Thursday question because it's going to take longer than I have to explain. But the short answer is Stata, you have to run it both ways, because one way gives you the test of whether you need the stretchy factor, but it doesn't give you the distribution fit. So NB-reg in Stata is negative binomial regression built in. It gives you a test of whether that K stretchy factor is needed, which means it's comparing it to Poisson, but it doesn't give you distribution fit. Whereas if I go back to GLM, it does give me distribution fit, but it doesn't give me the comparison to Poisson. So you got two different things to get all the pieces. But that's where we're going to end up on Thursday. Okay, 311. How are we doing, folks? Sideways? Okay, sideways is good. Sideways for the day after spring break, I will take it. Totally take that and run. Okay, then what should you be doing? What's next? I got to look at my own schedule.
Plan 4.
Yeah, homework plan. That's what's next. So please start working on that. It shouldn't take you very long if you know what data you want to use. If you haven't figured that part out, then it will take you longer. I have in the plan document links to several publicly available data sets that existed the last I checked. I can't promise that will continue to be the case, but they existed in that moment in time. If none of those work, go to your advisor, go to your lab and be like, hey, would anyone like some free data analysis? And let them hook you up, okay?
Is World Value Survey one of those that you have as a link?
I don't know if it is or not. I don't think
Because
so.
that one would not be impacted by our government, I don't think.
World Values Survey?
Right.
Okay, I will look into that.
Because yeah.
Okay.
It's what you think about, what do you think about this, that, and
There's a
value
lot of
stuff.
publicly
Yeah,
available
yeah.
data, and I really don't care what folks pick. Ideally, it would be something from your area of research so that you could make it into a further product. That's the motivation.
Will you say, when you look at the plans, if you think that we're biting off more than we
Yes.
should chew?
Yes, if you're trying to do too much, I will tell you.
Thank you.
Yes. Or if you have complicating factors that I haven't taught you how to address, like if it should be multi-level, whatever, like you can pretend it's not for the purposes of this.
Right. Well, because I think that mine actually would be kind of fun, because there's a little bit, I think you said a cluster effect in mine, but
Yeah.
that could be a fun thing to tweak next semester.
Yes, next semester. Yeah, exactly. One thing at a time. All right, 313, thanks for being here, Zoomers, Roomers. Let us know if you need anything. Hope to see you Thursday on Zoom. Okay? On Zoom. All right, bye for now.